watching session number 1 of the chapter Chemical Bonding and Molecular Structures. In this chapter, we are going to talk about the different types of chemical bonds formed and what about the structure of different chemical compounds and the molecular structure based on some theories. Let me start with the basic concept, that is what actually the chemical bond stands for. First, I am going to discuss what is chemical bond and why it is formed. What is chemical bond and why the chemical bond is formed. Okay, and we know that one matter consists of constituent particles and they are atoms and molecules. Remember, atoms combine, we are going to get the molecules. Why atoms combine? The reason behind that is atoms cannot exist independently in nature, whereas molecules can exist independently in nature. To attain the stable, that is molecular nature, the atoms combine and we are going to get molecules. If you observe any molecular structure, and we know that when the constituent particles are atoms and they are combined or joined, we are going to get a molecule. Then one can guess that there should be any kind of a force of attraction among these atoms so that the molecule is formed, isn't it? So therefore, the kind of force of attraction that holds all the constituent atoms in a molecule, and that we call it as a chemical bond. In short, I can say chemical bond is nothing but force of attraction that exists between the different atoms to form a molecule, and that force of attraction we call it as a chemical bond. So force of attraction or attractive force, you can say attractive force that holds constituent atoms, in a molecule, and that we call it as a chemical bond. So I told you that the atoms will combine and we are going to get a molecule, isn't it? And the question arises, why do atoms combine and why we are going to get a molecule and why there is the formation of a chemical bond? The question arises, isn't it? So now we'll see why actually atoms combine. So we'll see what would be the cause for combination, cause of chemical combination, we'll see, and the reason behind that we'll see, and we are going to get the reason behind that, why do atoms combine. Okay, so just we know from the fundamental concepts, all atoms in a modern periodic table, they try to attain the noble gas configuration. Noble gas configuration is nothing but the elements which have the octet configuration, which follows the octet rule. The elements which has 8 electrons in the outermost orbit of an element, and that is quite stable, and that property or that rule we call it as octet rule. And we know that valence electrons are nothing but the combining capacity of an element, in simple language you can say, but actually the number of electrons present in the outermost orbit of an element, and that we call it as valency. If an element has a total 8 electrons in the outermost orbit, and that configuration we call it as octet configuration, and the noble gas elements, that is inert gas elements, noble gases, they have the octet rule, they satisfy the octet rule, and they are said to be the elements with the noble gas configuration. The reason behind that is the elements which has a noble gas configuration, they are less reactive, or I can say they are inert in nature, they are quite stable, you can say. For this reason, the elements in the modern periodic table, they try to attain the nearest noble gas configuration to become stable. So that is the first reason why there is combination of elements, combination of atoms to form a molecule. You can say that is the first reason for the chemical combination, that is tendency to attain noble gas configuration, tendency of element to attain noble gas configuration. And one more reason is the stability of an element. If any element that attains the electronic configuration of nearest noble gas and that has less energy, so try to know that one, that has less energy, and because of less energy that is quite stable. So therefore the second reason is tendency of an element to attain a state of lower energy, that attains a state of lower energy. If it has a lower energy, and then we can say the particular element is quite stable. And if you consider all the elements in modern periodic table, they try to attain the electronic configuration of nearest noble gas. Usually the 18 group elements are, we know that one, helium, neon, argon, krypton, radon and xenon, and all these have noble gas configuration except one, and the element that is helium. And if you consider the helium, the number of electrons present in helium is 2. So that attains maximum of 2 electrons in the K shell only. Therefore, helium is said to follow duplet configuration instead of octet. Duplet, 2 electrons in the outermost orbit. So only helium has a duplet electronic configuration, and all the noble gases except helium, they have octet configuration, that is 8 electrons in the outermost orbit of an element, and any element that has 8 electrons in the outermost orbit, that is quite stable and that has less energy. Since it has less energy and that element is quite stable, so because of these two reasons, the atoms combine to form a molecule. The first one is tendency to acquire noble gas configuration. The second one is tendency of an element to attain the state of lower energy. Because of these two reasons, the atoms will combine and we are going to get a molecule. Since atoms combine to attain these two conditions, there will be a force of attraction among the atoms here, and that we call it as chemical bond. So we came to know what actually the chemical bond is and why do atoms combine. Okay, and now we'll see the different types of chemical bonds. The first one I am going to talk about, that is the ionic bond. So now I am discussing about the first bond, that chemical bond, that is ionic bond. And ionic bond you can call it as electrovalent bond also. Both are same, ionic bond or electrovalent bond. So we'll learn what is ionic bond. Okay, and in general the chemical bond we have different types. Ionic bond we have, covalent bond we have, coordinate or dative bond also we have. So we'll discuss one by one, and initially I am going to talk about what is ionic bond. So the final statement of ionic bond is the elements of atoms of an element, they try to attain a noble gas configuration with the state of less energy, we know. Because of these two reasons, the atom will combine, we know that one. Okay, so sometimes what happens here, some atoms have more number of electrons, some atoms have less number of electrons as compared to the octet rule. In that case what happens, some atoms try to share the valence electron, some atoms tries to donate the valence electron, some atoms try to gain the valence electron. So different kind of methods depends upon what kind of chemical bond is formed. Remember, in case of ionic bond or electrovalent bond, there is always a transfer of valence electron. Remember, there is a transfer of valence electron from one atom to the another atom. Valence electron only is going to be transferred. Okay, and there is no transfer of the electrons which are present inside, or you can say pre-nultimate shells. And valence electron is going to be transferred from one element to the another element. In some cases only one valence electron is going to be transferred, in some cases more than one also. So a chemical bond which is formed by the transfer of one or more electrons from one atom to the another atom to attain a state of less energy which is stable, and that chemical bond we call it as a ionic bond or electrovalent bond. The keyword is there will be the transfer of electrons. The keywords I am going to write here. Transfer of valence electrons. Transfer of valence electrons takes place from one atom to another atom, because to attain the noble gas configuration, to attain the state of lower energy. Some examples we'll see, then we'll come to understand one. Okay, and ionic bond, some examples are sodium chloride is an example for ionic compound. Okay, and MgCl2 magnesium chloride, KCl potassium chloride, and CaO calcium oxide. So all these are examples for the ionic compounds which has the ionic bond. And now we'll discuss how actually the ionic compound is formed. Okay, and now I am going to consider one example, that is NaCl. Okay, so we'll see how actually the NaCl is formed. The compound example I am going to consider, that is sodium chloride. Okay, so let me explain here how there is the transfer of a valence electron takes place, and because of there is a force of attraction between combining atoms, and that force of attraction we call it as the chemical bond, in particularly ionic bond. So let me explain that one. So now let me consider, I am going to consider the element that is sodium. Sodium belongs to the first group, we know that one, and atomic number of sodium is 11. Z represents atomic number and A represents atomic mass, we know that one. Z represents atomic number, and atomic number is nothing but the number of protons present in an atom. And for a neutral atom, the number of protons is always equals to number of electrons. So 11 electrons we have in sodium. So let me write the electronic configuration of that one. Electronic configuration: 1s2, 2s2, 2p6 and 3s1. So if you count the number of electrons, and number of electrons will be 11, that is the atomic number, and this is what actually the electronic configuration of sodium. One more element what we have, that is Cl, and the atomic number of Cl is 17, that is chlorine. Atomic number is 17. Let me write the electronic configuration of that, that is 1s2 and 2s2, 2p6, 3s2, 3p5 you are going to get, and if you count the number of electrons, that will be 17. So this is how I have written the atomic number and electronic configuration of sodium, and one more is Cl. So now here the element what I have represent, I am going to represent it by Lewis symbol, and that represents the number of electrons in the valence shell. Okay, that we call it as the Lewis symbol of representation of elements. So if you consider this electronic configuration, which is the valence shell, 1, this is the one shell, 2 is the second shell, and the 3 is the third shell. So the outermost or valence shell is 3s1, and here we have only one electron, and electrons are represented by dots, and they are supposed to represent the surrounding of the element here. So Na, one dot represents, and this dot represents number of valence electron in an element, that is sodium. And this kind of representation we call it as Lewis representation, L-E-W-I-S. While writing we write it as Lewis, but you should spell it as Lewis representation. In this case of Cl, totally there are 17 electrons, and now you guess how many valence electron we have. We have 1, this is the first shell, 2, this is second shell, and this is the third shell, 5, 6, 7, totally 7 electrons we have in the valence shell. I am going to represent that with dots here. So 1, 2, 3, 4, 5, 6 and 7. So 7 dots I represent, and that is the Lewis symbol for chlorine. So now what happens? Now we'll see how does Na combines with the chlorine, and what would be the product we are going to get, and we'll explain according to the conditions what I explained, that is the each and every element tries to attain nearest noble gas configuration with the state of low energy. So now you see here the number of valence electron is 1. If the sodium wants to be stable, that has to follow octet rule, means the number of electrons in the outermost orbit should be 8. But here in this case we have 7. So 1 electron we have, and here we have 7 electrons here. So the question arises, either this sodium, okay, so it has 1 electrons, means there should be either the presence of 7 electrons totally, you are going to get what actually 8, or one more chance is if this 1 electron has been lost, okay, and if 1 electron has been lost, what would be the previous shell? 2s2 and 2p6 will be the previous shell, 6, 7, 8, so 8 electrons we have already. So sodium is a metal, and we know that one metal has capacity of losing electrons. So to attain noble gas configuration or the octet rule, the sodium loses this 1 electron. So sodium is going to lose this 1 electron. To attain the noble gas configuration, 5, 6, 7, 7 electrons we have. So this Cl needs 1 electron to attain octet rule, isn't it? So what happens here? Sodium has 1 electron extra and Cl needs 1 electron. So what happens here? There will be a transfer of a valence electron from sodium to chlorine, so that what happens? There will be a stable molecule is formed. So this 1 electron is going to be transferred from sodium to chlorine here, and after that what we are going to get? We are going to get Na plus. You try to know that one. When Na becomes Na plus, when it loses 1 electron, and that after losing electron the cation is formed. And I hope you know that one. When an element loses electron, cation is formed. When an element gains electron, an ion is formed. So has lost 1 electron, therefore I will write Na plus. And in one more case we have Cl. So already we have totally 7 electrons. 1 electron is gained by Cl, so this is the 1 more electron gain, okay, and it has gained 1 electron. So what I should write here? I should write minus. Why I have written minus? Because it has gained electron, or in short you can say NaCl is formed. So in this manner there is a transfer of a valence electron from one atom to another atom to get a state of less energy, and that kind of force of attraction or a chemical bond we call it as ionic bond. Therefore the ionic bond is defined as the chemical bond which is formed by the transfer of 1 or more electron from one atom to another atom, that we call it as a chemical bond. In this example of NaCl, only 1 electron has been transferred, therefore there is involving or the transfer of 1 electron takes place to form the ionic compound called sodium chloride. One more example we'll see. The one more example I am going to consider for the formation of ionic bond, that is MgCl2, magnesium chloride. So we'll see how actually magnesium chloride is formed and the reason behind why this belongs to ionic compound. So magnesium I am going to consider, and I hope you remember the atomic number of magnesium is 12. Magnesium belongs to the second group after the sodium. We are going to get the magnesium atomic number is 12. And now we'll write the electronic configuration of that. That is 1s2, 2s2, 2p6, 3s2 we are going to get. That is the electronic configuration of magnesium. So if you consider this one, the number of electrons present in the outermost orbit, that is valence electrons, are 2. So what I have to do? I have to represent it by 2 dots. These 2 dots represent the number of valence electrons in magnesium. And the one more element what we have, that is Cl. But how many Cl we have? 2 we have Cl. So therefore 1 I am going to write here. And we know very well that I explained already the number of electrons. Here it is 17 and the number of valence electron will be 7. I will write it directly. So 1, 2, 3, 4, 5, 6, 7. That is the Lewis dot symbol for chlorine. And similarly, since 2 Cl are there, therefore I am going to write this electronic Lewis dot representation. So now we'll see what happens when these two will combine. And now you see these elements also try to attain the noble gas configuration by following the octet rule. Now if you observe magnesium, that has to get 8 electrons in the valence shell, so we have 2 electrons already. So this magnesium, if it loses 2 electrons, and the previous shell will be, that is 2s2 and 2p6, and that has 8 electrons. So from this one can guess that magnesium has capacity of losing 2 electrons. Okay, whereas in this chlorine we have 7 electrons already, so one Cl needs 1 electron to follow the octet rule, and this Cl also needs 1 electron to attain the octet rule. So this Cl needs 1 electron and this Cl needs 1 electron, one electron each the Cl needs, whereas Mg has 2 electrons. So what happens here, this Mg, 1 electron is given to this chlorine and 1 more electron is given to 1 more chlorine. Therefore what happens, there is a transfer of 2 electrons from magnesium and you are going to get a Cl here. In short, I can say magnesium loses 2 electrons and these Cl gains 1 electron each from magnesium. So how I am supposed to write? I told you that when any element loses electrons, we are going to get cation. How many electrons it has lost? 2. Therefore I am going to write Mg2 plus Cl. This is 1 Cl. 1 Cl gains 1 electron. Therefore minus I am going to write. Since 2 Cl are there, I can write 2 here, or in general the formula will be MgCl2. Okay, this is how the MgCl2 ionic compound is formed by transfer of 2 electrons. In the previous case of sodium chloride, there is a transfer of 1 electron, isn't it? Whereas in this case, the Mg loses 2 electrons and 2 Cl gains 1 electron each to attain the stable noble gas configuration that has to follow the octet rule. Okay, and this is how MgCl2 is formed, and that is the one more example for ionic compound. So ionic bond, there will be a transfer of valence electron only to attain the noble gas configuration. In a particular nearest noble gas configuration, you can say, I told you that only one element we have that won't have actually the noble gas configuration, that is helium. Because if you consider hydrogen, okay, so hydrogen is the first element, so hydrogen won't try to attain octet configuration because the noble gas which is nearer to hydrogen is helium, isn't it? And helium has duplet, isn't it? So hydrogen tries to gain the duplet configuration, that is 2 electrons here. So this is the reason in each and every elements what we have in the modern periodic table, they try to attain the nearest noble gas configuration to be stable. And to attain that nearest noble gas configuration, if there is transfer of electron and that kind of chemical bond, we call it as ionic bond. Okay, so this is, I can generalize the meaning of ionic bond with examples. Similarly, you can process kind of the structures for KCl, calcium oxide, and n number of ionic compound examples. So now after knowing the meaning of ionic bond and example, now I am going to discuss about the factors favoring ionic bond formation. So here I am going to talk about the factors favoring ionic bond formation. So what are the very important factors that need to form a ionic bond? The first one we'll see. The first one is ionization energy. Ionization energy. You can call it as ionization potential also. Ionization enthalpy, the same thing. So we'll see what is the first factor that is going to affect the formation of ionic bond. The first one I have written already, that is ionization energy. Ionization energy means the minimum energy required to remove the valence electron from gaseous atom, we call it as ionization energy. So try to know, if we consider an atom, particularly gaseous atom, if the outermost electron is going to be removed, we need a minimum energy, isn't it? The kind of energy to remove the valence electron, we call it as ionization energy. One thing you remember, in case of ionic bond formation, the ionization energy of element should be low. Remember that low ionization energy favors ionic bond formation. And the question is this: why low ionization energy is favored? Okay, remember, if you consider any atom of an element, if it has a low ionization energy, means the outermost electron of that atom can be easily removed. Or in one more sense I can say that particular element has capacity to lose electron very easily, isn't it? So if an element loses electron and that forms a cation and the lost electron is gained by anion, we know that. So since if the element has a low ionization energy, that will be good, or that is the favoring condition for the formation of ionic bond. So if with respect to equation, if you want me to write, so let us assume A is the one atom of an element, and if it loses an electron, we are going to get A plus in general. After losing electron, the energy involved, I write here, what is that? Ionization energy. So try to know that one. When atom loses electron, we are going to get a cation. So A has lost one electron, therefore I have written here A plus, and the energy involved in that is ionization energy. Remember, for ionic bond formation, low ionization energy is required. Second one is electron affinity. Electron affinity. One more name we have, that is electron gain enthalpy. Both are same, electron affinity or electron gain enthalpy. So we'll see what is the meaning of electron affinity. If you consider an atom of an element and you are going to add one electron to the valence orbit, during that process the amount of energy released, that we call it as electron affinity. The amount of energy released when an electron is added to outermost orbit of an gaseous atom, that we call it as electron affinity. So we'll link with how actually this is going to help for the formation of ionic bond. Remember, metal loses electron, if you consider as an example, and that electron has to be gained by one more atom, isn't it? And if electron affinity, electron affinity is high, means it has a very good capacity or favorable condition of gaining the electron, then that lost electron is easily gained by the atom of an element. Therefore electron affinity should be high. So what I am going to write here, the element should have the high electron affinity. So what happens here, let us assume B is the one more atom, and what happens, A has lost one electron and this electron is gained by the B, and in that case what happens here, B minus an ion is formed. I told you that if there is a gain of electron, an ion is formed, and during this process a energy is released, and that we call it as electron affinity. You try to know that one. So we need a high electron affinity, and the previous one was we need a low ionization energy for the formation of ionic compound. We'll see the third condition. The third condition is lattice energy. So how lattice energy is involved in the formation of a ionic bond? So we'll see that one, what actually the lattice energy stands for. So let us assume one cation we have, that is A plus. This is how actually the A plus is formed, and one more anion is B minus. By gaining electrons we got B minus. So these are the constituent ions, you can say. So cation, anion, they are going to combine, and we are going to get a ionic compound AB, let us assume. And during this reaction the energy involved, that is represented by U, and that we call it as the lattice energy. So lattice energy is nothing but when 1 mole of ionic compound is formed. Remember, mole, that represents the amount of a substance, isn't it? So when 1 mole of ionic compound is formed by the combination of constituent ions, they are cations and anion, and the energy released in that reaction we call it as the lattice energy. Remember, high lattice energy is required for the formation of ionic bond. Remember, higher the lattice energy, greater will be the stability of ionic compound. I repeat, higher the lattice energy, greater will be the stability of ionic compound. Why? Because the tendency of the combining of cation and anion will be more to form the ionic compound, and the energy involved or energy related to that formation, and that we call it as lattice energy, and high lattice energy required for that one. That is the condition number 4. Now we'll see the condition number 4, that is the number of valence electrons. number of valence electrons. So how number of valence electrons helps us to see the formation of ionic bond. Let us assume A and B I have. So A is going to be formed cation by losing electrons, and B is going to be formed anion by gaining electrons. So if A has usually 1, 2, 3 as the valence electron, the formation of ionic compound will be more, and 5, 6, 7 valence electron it have, then the formation of chances of ionic compound will be more. See here, the A, or you can say the metal, okay, that either have 1 electron or 2 or 3 valence electron if it has, and similarly B, 5 electrons or 6 electrons and 7 valence electrons if you have, and the chances of the formation of ionic compound will be more. So these are the factors favoring the formation of ionic compound. So totally 4 factors I explained. So just to see, the first one is ionization energy, second one is electron affinity, the third one is lattice energy, and the fourth one is the number of electrons. So in short I can say, for the formation of ionic compound, low ionization energy is required, high electron affinity is required, lattice energy should be high, and the number of electrons of the constituent ions may be 1, 2, 3 for the A and 5, 6, 7 for the B, or I can say one is metal and one is non-metal. Okay, and these are the factors favoring formation of the ionic compounds. So now after knowing the factors favoring the formation of ionic compounds, now I am going to discuss about what about the properties or the characteristics of ionic compounds. So now I am going to talk about the properties. Properties of ionic compounds. So what are the physical properties of ionic compounds? We are going to discuss, and based on the factors favoring also we know, and we know the basic the concept about the ionic bond. The first one I am going to talk, that is the physical state. The physical state. So how actually the physical state of ionic compound will be? Okay, so remember, if you consider sodium chloride as an example, remember sodium chloride is crystalline solid. Okay, and 1 Na plus is surrounded by 6 Cl minus. If you observe the crystalline structure of sodium chloride, which is body centered cubic, actually 1 Na plus is surrounded by 6 Cl minus, and 1 Cl minus is surrounded by 6 Na plus. This is how the cations and anions are arranged. In short, I can say, in ionic compounds, the physical state will be in the form of ions here. So remember that the physical state will be ions, cations and anions. On the contrary, in case of covalent compounds, the physical state will be molecules. This is the main difference you try to know. So in ionic compound, one can guess the physical state will be in terms of ions itself. The second one will see, what about melting and boiling point? What about melting and boiling point of ionic compounds? So melting and boiling point. So first we will see on what factor actually the melting point and boiling point is related. Remember that melting point and boiling point depends on the kind of force of attraction between the constituent particles. So in case of ionic compound, in case of electrovalent compound, the force of attraction is quite strong, and that we call it as electrostatic force of attraction. And I use the word called electrostatic force of attraction because we have cation and anion, the ions of the opposite charges, and they are separated by a distance. Therefore I use the word called electrostatic force of attraction. Since we have strong electrostatic force of attraction, and that is quite strong as I said, and we need high energy to break that. If you want to disturb the what is the crystal structure, the ionic structure in a crystal, we have to destroy or we have to rupture the force of attraction between cation and anion. That is quite strong. We call it as electrostatic force of attraction. So we need a high energy. So if we supply high energy, and that force of attraction is going to break, and therefore I can say we need high melting point and boiling point. So ionic compounds have high melting point and boiling point. The reason behind that is the force of attraction is electrostatic force of attraction. In simple you can say. Next we will see, after the melting point and the boiling point, we'll see what about solubility, how it is going to be soluble in solvents. So here what I am going to write, the ionic compounds they are soluble in polar solvents. They are soluble in polar solvents and they are insoluble in non-polar solvents. They are insoluble in non-polar solvents. So this is the final term we need to know. Ionic compounds are soluble in polar solvent. Let me give some example for polar solvents. H2O, water is a polar solvent. HCl is a polar solvent, and liquid ammonia, this is also polar solvent. Non-polar solvent example, the organic solvents, benzene and CCl4, carbon tetrachloride, all these are the examples for non-polar solvents. So first we will see what actually polar solvent stands for, what actually the non-polar solvent stands for. In case of polar solvents, as the name indicates, polarity we are going to observe. In case of non-polar solvents, we are not going to observe polarity, but the actual meaning is, in case of polar solvents, we have high value of dielectric constant, whereas in case of non-polar solvents, we have very less value of dielectric constant. And then question arises, what is the function of dielectric constants? Remember, in polar solvents, I told you dielectric constant it has. So dielectric constant that reduces or ruptures the force of attraction between the ions. Since polar solvents have high dielectric constant, that helps to rupturing or reducing the force of attraction between cation and anion. The cations and anions in the ionic compound, they are free. Then what happens? That reacts with the solvent, so that is a soluble in a polar solvent, what we can say. Whereas in case of a non-polar solvent, I told you that very less value of dielectric constant we have. So since less value of dielectric constant, so because of that there is no reducing or rupturing of force of attraction between the constituent ions, therefore they are insoluble in non-polar solvents. So that is the reason behind that, but in simple, remember, the ionic compounds are soluble in polar solvents, whereas ionic compounds are insoluble in non-polar solvent, and that mainly depends on dielectric constant. And remember, water has the highest dielectric constant, and if you mention me the value, if you want to mention the value, that is 80 is the dielectric constant. Therefore, water has a maximum capacity of dissolving the solute, therefore water is called universal solvent since it has high dielectric constant. That is about what actually the solubility property. Next one we'll see, what about the electrical conductivity? Electrical conductivity of ionic compounds. So now I will give one example, then you will understand. If you consider solid sodium chloride, and if you consider molten sodium chloride, when I considered solid sodium chloride, and one more is a molten sodium chloride, and I told that one in a solid sodium chloride, there is a definite arrangement of cations and anions in a crystal structure. So these ions are not mobile in nature. These ions are fixed in a particular crystal structure. Whereas in case of molten ion, so how you are going to get a molten ion? If you consider solid sodium chloride and if you supply heat, then what happens? That heat is absorbed by the cations and anions, so that the kinetic energy of the ions increases. They start moving in the different direction. Therefore, in case of molten sodium chloride, we have mobile ions. So try to know that one. In case of molten sodium chloride, we have mobile ions. You can consider aqueous sodium chloride also, the same thing. Aqueous sodium chloride. Sodium chloride is dissolved in water. A solution where water acts as solvent, we call it as aqueous, the same thing. So if you dissolve sodium chloride in water, so the mobile ions we are going to get, Na plus and Cl minus, they are going to be separated from the crystal structure. Since the presence of mobile ions we are going to observe in molten sodium chloride or aqueous sodium chloride, and that has capacity of conducting electricity. Remember, for any substance to conduct electricity, either there should be a presence of mobile electrons or mobile ions. In case of metallic conductors, we have mobile electrons. In case of electrolytic conductors, we have mobile ions. In this case, there will be the presence of mobile ions, so that the molten sodium chloride or aqueous sodium chloride conducts electricity, whereas in case of a solid sodium chloride, that won't conduct electricity even though the ions are present. And try to know, the ions are not mobile in nature, they are not free, they are not moving in the different direction. Because of that reason, what I can say, the solid sodium chloride is a bad conductor of heat and electricity. That is the one more property, that is electrical conductivity. So all these are the properties of ionic compounds. So physical property, and one more is the melting point and boiling point, and solubility, and the last one is electrical conductivity. In short, you remember the physical state in terms of ions, it will be present, whereas in case of melting point and boiling point, high melting point and boiling point is the property. In case of solubility, soluble in polar solvents and insoluble in non-polar solvents. And electrical conductivity, solid ionic compounds, bad conductor of heat and electricity, whereas the molten or aqueous ionic compounds, good conductor of heat and electricity. And the reason behind all the four properties I explained. Okay, so that is all about the properties of ionic compounds. So here I explained the factors favoring and I explained the properties of ionic compounds. And now we'll see some other terms that explains the stability of ionic compounds. We'll see that one by one. I am going to talk about the energy involved. As I mentioned, that is lattice energy. So we'll see what is the lattice energy stands for, and how the lattice energy is going to define the stability of ionic compounds. As I told you already, and one example I am going to give you, when Na plus combines with the Cl minus, and we are going to get a sodium chloride crystal in the form of a solid. We know that Na plus is formed by the loss of 1 electrons from sodium. Cl minus is formed by the gain of 1 electron from Cl, which is lost by Na. We know that one. So these two are in gaseous form only. So the lattice energy E means the energy released when 1 mole of a solid ionic crystal is formed by the combination of its constituent atoms which are in the gaseous state, constituent ions which are in the gaseous state, and that energy involved, we call it as the lattice energy. The amount of energy released when 1 mole of ionic compound is formed from its gaseous constituent ions, you can say, and that is the meaning of lattice energy. And remember, the one more very important point is, let us assume we have a lattice energy, and the lattice energy of a compound is very high. So if the lattice energy of compound is very high, then what happens? The stability of ionic compound is also very high. This relation you need to know. When the higher the lattice energy, more the stable ionic compound is. I repeat, higher the value of lattice energy, greater will be the stability of ionic compound. If we have the ionic compound with very less lattice energy, and that is not stable or unstable, you can say, this is how the lattice energy and the stability of ionic compound is going to be dependent on. And if the lattice energy should be high, then what are the two conditions? When the ions will combine, you are going to get an ionic compound where the lattice energy should be high. The first one is, we need a small ionic size. So ionic size of the cations, anions should be small, and one more is the charge should be very high. Charge should be very high. So if any ion satisfies these two conditions, and one can imagine that by combination of the ions of these two conditions, we are going to get an ionic compound with greater stability. Ionic size should be small. Ionic size is nothing but the distance between electron present in the outermost orbit and the center of the nucleus of ions, and that we call it as ionic size. The smaller the ionic size, then the chances of high lattice energy is going to be favored. One more is small size with a high charge. The charge, that may be positive or negative, the charge should be quite high so that the lattice energy will be high, so that we are going to get a ionic compound with quite stable. So that is how the lattice energy is going to relate with the stability of ionic compound. And one more condition or one more factor that relates with the stability is solvation energy. So we'll see how solvation energy is going to explain the concept about the stability of ionic compound. So we'll explain that one. What is the solvation energy? So we'll say what is actually solvation stands for. Let us assume I have a solvent. The component in a large proportion, we call it as solvent, and I am going to add one substance to that. So what happens? There will be interaction of substance with the solvent. So interaction of substance with the solvent, we call it as a solvation, remember. And the energy released or energy involved during the solvation, we call it as solvation energy. See here, solvation is nothing but interaction with the solvent. Interaction with the solvent, and the corresponding energy is, we call it as a solvation energy. That is the solvation energy. In simple, I can say the energy involved when a substance is going to interact or when a substance is introduced into a solvent, and that we call it as solvation, and the energy involved we call it as solvation energy. So solvent, I said, so solvent may be water or liquid ammonia, liquid sulfur dioxide, HF, etc. So if you consider water as a solvent, and then we don't use the word called solvation. Instead of that, we use one more word that we call it as hydration. So try to know that one. So hydration is the word going to be used when water is going to be the solvent. When water is a solvent, hydration, the word is going to be used. Of course, the main function of the solvation and hydration will be the same, but if water is used as solvent and the hydration word is preferred. Or you can say the process involved, we call it as hydrolysis. So what is hydrolysis? The interaction of a cation and anion of a substance with the cation and anion, or you can say H plus and OH minus of the water, and that we call it as hydration. In simple language, I can say when a substance is introduced into the water, the interaction between the substance and water, that we call it as hydration. I told you already, the solvent is water here, therefore hydration word is going to be preferred. So this is the concept what actually the solvation, hydration and solvation energy stands for. So now we'll come to how actually we can explain the stability of ionic compound here. So if any liquid, so let me write here, if any liquid with high dielectric constant, high dielectric constant, if we consider any liquid with high dielectric constant, and what I am going to say here is that is going to be soluble, that ionic compound is going to be soluble in the solvent. And if any liquid, okay, with low dielectric constant, with low dielectric constant, and now I am going to say that in that case the ionic compound is insoluble in the solvent. So this is the final and very short term to remember I explained here. And if any liquid has a dielectric constant, the ionic compound is going to be soluble in the solvent. If the liquid has a low dielectric constant, that ionic compound is insoluble, or that is not going to be soluble in the solvent here. And I hope you can the connect with the reasons what I explained already. High dielectric constant, if any liquid has a high dielectric constant, means that dielectric constant helps for the reduction of electrostatic force of attraction between the ions, and therefore the ions of the ionic solid that may interact with this solvent so that the ionic compound is going to be soluble. Whereas if there is no dielectric constant or low dielectric constant and that dielectric constant fails to reduce the electrostatic force of attraction between the ionic solids, that case what happens here, that particular ionic solid is insoluble in water. So this is how, based on the solvent what we consider, from that we can guess whether the given ionic compound is soluble or not here. And I told you already, the ionic compounds are soluble in polar solvents like water. I told you that one. So why it is soluble in water? Because water has a high dielectric constant. That water reduces the electrostatic force of attraction between the constituent ions of the ionic compound, therefore the ionic compounds are soluble. This is how in short I can write here. So one more relation I can write, delta H of hydration energy. If delta H of hydration energy is greater than delta H of lattice energy, then the ionic compound is going to be soluble. If delta H of hydration energy, is less than delta H of lattice energy, and now you can say the ionic compound is going to be insoluble in the solvent here. So by these two conditions also you can explain whether the ionic compound is going to be soluble or not. That depends on what actually the amount of delta H hydration energy takes place or not. So let me repeat that one. Liquid with a high dielectric constant that causes solvation, you can say, or you can say that is going to be soluble. So this causes solvation. So soluble, you can say there will be solvation, whereas in this case there is no solvation, I can write in short. So if there is a solvation, then you should consider a such liquid which has a high dielectric constant, and if there is no solvation or no hydration, the liquid should be of low dielectric constant, and in this case there will be solubility of ionic compound, and in this condition there is insolubility, or the ionic compound is not going to be soluble in the solvent, or you can say water if you consider. That is how we can explain the lattice energy and solvation energy, and using that we can explain the stability of ionic compound and whether the ionic compound is soluble or not. Now we'll see lattice energy. I told you, so how we can calculate lattice energy practically. So lattice energy of ionic crystal can be calculated by one equation and one formula, and that we call it as Born-Lande equation. Born-Lande equation. So Born and Alfred Lande, so they are the scientists who are the pioneers in case of deriving the equation to calculate the lattice energy of a ionic crystal. Remember, Born-Lande equation helps us to calculate lattice energy of ionic crystal. So what is the final equation I am going to write here? So U0 represents lattice energy of ionic compound. So U0 equals minus Na Z1 Z2 E square divided by R into 1 minus 1 by N. So this is the mathematical form to calculate the lattice energy of ionic compound, and that we call it as Born-Lande equation. So you just remember this equation, and we have the problems based on this equation also. U0 is equals to minus Na Z1 Z2 E square divided by R 1 minus 1 by N. We'll see what are these terms involved. So let me write that one. U0 is the lattice energy. Okay, and we have N, and I hope you know N is nothing but Avogadro's number, and we know the value of that. And A is the new quantity, and A we call it as the Madelung constant. A is nothing but Madelung constant, and we have Z1E and Z2E. If you observe the equations here, Z1E we have and one more is Z2E. Z1 is cation if you consider, and Z2 will be anion, and that will be the charge of cation, and one more will be the charge of anion you can consider, and we have one more, that is R, that is nothing but ionic distance, the distance between the cations you can consider, and last we have N, and that is the Born exponent, that is a constant, Born exponent. So we have two, the constants, one is A, that is the Madelung constant, and one is N, small n, and that is Born exponent here. So that is the terms involved in the Born-Land equation, and now all these terms, the meanings we know that one, okay. U, lattice energy we know, and Avogadro's number we know that one, and the charge of cation, charge of anion, total ionic distance, and A is different and N is the new things for us. So let me explain what is this A stands for, and directly we say that one, A is a Madelung constant, similarly N is a Born exponent. So now I will explain you what actually the Madelung constant is. Let me consider one example, that is a sodium chloride, and we know that one Na is surrounded by Cl minus ions, strictly 6 Cl minus ions, and 1 Cl is surrounded by 6 Na plus ions. This is how the crystal structure is formed, and that will be body centered cubic crystal structures we know. Let us assume I have one cation, in general one cation, and it is surrounded by anions, I told you that one. So these are the ions of opposite charges. We know that one, ions of opposite charges, they attract each other. So there is a force of attraction between positive charges and negative charges. But remember, the ion is not only attracted by one ion of the opposite charges, but also attracted by some other counter ions, some other the anions you can say, that of opposite charges. So what happens here, there is not only the attraction between one cation anion, but also attraction of cation from the counter ions. We use the word called counter ions. Counter ions means ions which are surrounding and the charge will be opposite, and that we call it as a counter ion. So there is a net force of attraction in the ionic solid. That net force of attraction is represented by a constant, and that is actually Madelung constant. Know this. One more is Born exponent, and we have positive ion and negative ion. We know that one. Sometimes there will be one more positive ion also. So what happens here, if you consider the positive ion and positive ion, same charges we have, there is a repulsion between that. So of course there is a force of attraction between ionic solid, some kind of repulsive nature will be present, and that is represented by a constant, and that we call it as N, and that is actually what actually the Born exponent is, and that is how this equation we call it as the Born-Land equation, and that is the mathematical equation. Remember, U0 is equals to minus Na Z1 Z2 E square divided by R into 1 minus 1 by N, and if you calculate that, we are going to get the lattice energy. Remember, if you get high amount of lattice energy, and one can say that the given ionic compound is quite stable. And that is about the concepts what we studied in this session. In the next session, we'll discuss about some other concepts related to ionic compounds. Thanks for watching.